This is my graphics programming app, and on the right we have a regular 2D canvas sketch, and on the left we have a WebGL sketch, which uses shaders instead of functions to filter all the images. Here we have the original webcam feed on both of them in this cell here, and we can capture a webcam image in the normal version because it's more difficult for it to process all of these filters at the same time. You can also clear and recapture an image. This is a live feed so that it can show off the live face recognition, and that it works better without being a live feed. This is due to the Gaussian blur function. As you can see, it's very computationally intensive, and we're missing our request animation frame window, and the same thing happens with the pixelate. And you can see we get a little staggering, so I'm going to switch away from that for now. You can change the filters on both of them by using the input keys. 1, 2, 3, 4, 1. Okay, so first we get the input image, and then that's used as the input of this one, which increases the brightness by 20% and converts to grayscale. Goes over every pixel, multiplies every channel of the pixel except for the alpha value by 1.2. That increases the brightness, and then it uses the weighted grayscale values to average the value of the RG and B channels, and then it puts that average value back into all RG and B values, giving us a grayscale image. Similar thing happens in the shader, but the shader uses the grayscale weights, and it does the dot product of every pixel it samples with that. Now down here we have the separate RG and B channels, and if it's not the desired channel value, those are set to 0. So for this one, goes over all of them, sets all the green and blue to 0. This one sets all the red and blue to 0, and this one sets all the red and green to 0. This uses a vector 3 as a mask, and so for this one, the first value is 1.0, the rest are 0.0, and then the second one's for the green, and the third one's for the blue. It just multiplies by that mask, and if there's a 1, it keeps the value, and if there's a 0, it's not. So alternately, you could combine these and mask out a single channel. Now, for the thresholds on both of them, they take the above channels as inputs, and then they apply the threshold value based off of these adjustable slider values. They take the outputted result from this buffer, and then they go over every pixel again, and they determine whether there any value in any of the channels is above the threshold, and if it's not, it's set to 0. It uses a step function based off the threshold value to create a mask, and then it multiplies by that mask. If it's above the value, the mask's value becomes a 1, and if it's not, the mask value becomes a 0 with the step function. The output of the step function is 0, either 1 or 0. These are duplicate feeds. This is a still image. Then here we have our color spaces, where this is the HSV color space, and this is the CMY color space, which is just the negative RGB color space, really, the inverse. And this one goes over every pixel and applies the function provided to convert to HSV, which is those series of ifs, else's, and converts it to HSV, and then puts those values back in the RGB values directly. And this one does the same thing. It calculates the CMY values and then puts them back in the RGB. And then these are just 2 more thresholds that inherit the input from above and do the same thresholding as above. Same with down here. The shader code for this one here, the HSV, is a little more complicated. It does a branchless way of applying the conversions, the if else's, but the output is the same, and then it just does the 1 minus for this one as well. So pretty straightforward in the shader as well. Just gets to do it in parallel across thousands of pixels at the same time. Now the pixelation for the shader is a lot more interesting than the pixelation from the normal filter. The normal filter goes over every pixel and the neighbors that all are within the same pixel block, and then averages their values and then writes. Whereas this pixelation, what it does is it takes advantage of the MIP mapping that's provided by P5 and WebGL drawing context, and it just samples lower and lower MIP levels, and so lower and lower levels of detail, and you just get the pixelation there for free. And it's just done by which texture it samples based off of the MIP bias you give it. And then the Gaussian blur on it goes over the nearest neighbors, and it does an n by n convolution function, and it does the Gaussian matrix, applies it every pixel. Whereas the shader, it does a 2-pass, first horizontally just doing the n neighbors, and then vertically doing the n neighbors. And once you do that one after another, you get the same results with much fewer samples. And then it also takes advantage of linear interpolation between pixels by sampling between pixels instead of the pixels themselves. So it interpolates between multiple pixels. So it leverages some GPU functionality to get a little bonus there. That's my